Good morning, everyone. Welcome to this webinar Beyond LCR Measurement, Validate Passive Components under Real Operating Conditions. My name is Roy Hali. I'm Senior Application Engineer at HIOKI Europe. And today I'm joined by two of my Japanese colleagues, Nao-san and Saito-san. Nao-san is product marketing engineer components at the headquarters in Japan, and he will take the most of the presentation, or he will present the technical part of this presentation. And also Saito-san has joined this webinar. He will also participate in the Q&A session of this webinar. So both of them are very experienced on this subject and can answer your live questions later on. This webinar is basically a follow-up of a webinar that we had on June 9th. For those who have followed that, then you know that in that webinar, we looked at measurement of component testing with LCR meter and impedance analyzer and gave some useful tips. With this in mind, this basically the structure of the webinar is the same. We're going to give you useful information about how to measure and also give you tips how to get the best results. But before we're going to start, I'm going to explain a little bit about the structure of the webinar. And with that, we go to the next slide, please. The webinar will take roughly 45 to 60 minutes. That is depending on the questions, the amount of questions that we will receive during the webinar. You are all muted during the session. So if you have any questions, please use the Q&A section that you can find at the bottom of your screen and enter your questions during the webinar. Depending on the number of questions, it could be that we don't have enough time to answer all the questions during this session. But don't worry, all the questions that are put in the Q&A box will be answered in writing also. Of course, this video is recorded and the link will be provided to you all later on. And then we go to the next slide. First, a brief introduction of the company HIOKI. We have been founded in 1935, so 91 years old at this moment. And we started manufacturing electrical indicating meters. Roughly 1,200 people work for the company, and we are on the Tokyo Stock Exchange, and the company is a very engineering-driven company. And two very good examples of that are present with us today. All the products are manufactured in Japan, and since 2017, we also have the European headquarters in Eschborn in Germany, and we work with different partners all over Europe that support us in the business. If we then look at what kind of equipment HIOKI is providing, please go to the next slide. Then you see here a broad overview of the products that HIOKI is supplying, and that starts from small multimeters and clamp-on meters that are being used by installers to manufacturing test equipment. And for that, you can think about battery testers, LCR meters, impedance analyzers, and power meters. For research and development, we also have different products like data acquisition systems, memory recorders, and power analyzers. And these are all combined with one of the core technologies that HIOKI has, which is the current sensing. We are very strong, and that gives us a very good opportunity in the market. All right, then we go to the next slide. But before we're going to start the real session of this part of this webinar, we will have a short poll. And we ask you to fill out the questions in this poll. And after that, we will move on with the technical part of this session. I see that the answers are coming in already. And I see that the major part of the participants, they are involved in research and development. It's about 40% of the people that are taking part of that. And also power supplies is prominently there, and management and planning is also available. And for the second question, most of the answers are the first answer that you can see, yes, I do it regularly. So the measurements that we are going to present. Okay, then I would like to move on with the webinar. And I will close the Q&A or the poll for now. Then here you can see the title of the second session, Beyond LCR Measurement, Validate Your Design Under Real Operating Conditions. And I would like to invite Naosan to take it over and to start with your presentation.
All right. Thank you, Roy. And again, I'm Nao. I'm from HIOKI headquarters. And today, in this webinar, I would dive into impedance measurement under real operating conditions. So we have received quite a few inquiries on this topic recently. The rise of EVs and data centers has significantly changed the requirements for power distribution systems. This shift is driving the need to evaluate components under real operating conditions. So today I will start by introducing the latest market trends, followed by the main topic, including a demonstration. So I'll also share 8 tips for achieving accurate measurements. So please stay tuned. All right, let me get a pointer. So let me start by introducing the market trends and how system requirements are changing along with them. So according to IEA, International Energy Agency data, if we look at global new car sales from 2000 to 2024, you can see that since around 2020, the share of electrified vehicles has been expanding rapidly. And for data center electricity consumption from 2020 to 2030, the projection is for a dramatic increase driven by AI-related workloads or servers. This is happening from 2024. And we can see these two trends, industry trends, and there are 4 key system requirements emerging related to these. So first one, higher voltages. Bus voltages are rising to improve power transmission efficiency. Second, higher power density. In EVs, it's about extending driving range through weight reduction. In data centers, on the other hand, it's about shrinking the physical footprint through higher integration. Third, higher efficiency. reducing energy losses to boost EV performance and address thermal challenges in data centers. And fourth, faster power delivery. There's growing demand for power systems that can handle the rapid load transients you see in autonomous driving and AI data servers. So the takeaway here is that the expansion of EVs and AI data centers is fundamentally changing what's expected from these systems. So next, let me walk you through the changes and challenges at the power supply and the system level more in detail. So there are four changes happening at the system level. The first one, a higher voltage system. And both EVs and data centers are transitioning from 400 volts to 800 volt architectures. In EVs, the push is driven by charging efficiency and weight reduction. In data centers, NVIDIA has proposed 800 volt architectures for more efficient power transmission. This has an impact on reducing failure modes and saving on cable footprint. So this adoption is expected to grow. But with this voltage increase, basic essential performance and surge withstand capability become major challenges. And the second change is the high power density system. And as systems become more compact and lightweight, higher integration is creating localized stress, and heat generation and cooling are becoming real issues. Third, the adoption of wide bandgap devices, SiC and GaN power semiconductors, they delivers more efficient power conversion through faster switching. But on the flip side, this increases high frequency losses, electrical stress from high dV/dt during switching and switching noise. And issues that were virtually invisible before, like high frequency loss analysis, premature degradation of essential systems, and electromagnetic interference with surrounding components are now front and center. So fourth, the demand for faster power delivery. So AI computing creates load transients of hundreds of amperes within nanoseconds. The challenge is achieving both high-speed transient response and stable steady-state power performance. So the requirements placed on power transmission circuits and the power supply systems are changing dramatically, and the performance expected from the components used in those systems is changing right along with them. So in the next slide, I'll show you the actual power transmission circuits and the key components that are used in those circuits. So this is just an example of a power transmission circuit using a data center power architecture. Three-phase power comes in from the grid and is converted to DC 400 volts or 800 volts by the AC to DC converter. After isolated DC to DC converter, the voltage is stepped down to 48 or 54 volts. And non-isolated DC to DC converters generate the voltages each load needs, roughly 0.6 to 12 volts. The key components supporting these power conversions are transformers, diodes, FETs, capacitors, inductors, and thermistors as well. Thermistors have also been gaining a lot of attention as thermal management becomes increasingly critical. So by thoroughly understanding the performance characteristics of each component, we can design power supplies with fewer design iterations and less rework. So traditionally, LCR meters and impedance analyzers have been the go-to instruments for evaluating component performance. But as systems continue to demand higher currents, there's growing attention on evaluating component performance under actual operating conditions. So this is something that has been difficult to capture with these conventional instruments. From the next slide, I'll walk you through the evaluation of components under real operating conditions, focusing on power inductors, starting with wide motors, and then covering how to select the right instrument for this evaluation, and also some tips to achieve accurate impedance measurement or loss analysis. So first, with a typical inductor application, we'll see where inductors are used. This is again typical an example of an electrical circuit using an inductor is the boost chopper circuit in a DC to DC converter. In this circuit, energy is stored in the coil when the switching device is on, and when the device turns off here, the stored energy is released together with the input voltage. So that results in the output voltage higher than the input voltage, right? So this technology has traditionally been used to increase the motor output in hybrid electric vehicles, but in recent years, its use has also been expanding in electric vehicles, EVs, and fuel cell vehicles. Additionally, boost chopper circuits are widely used to increase the panel voltage in solar power generation systems. Silicon Si is commonly used as the switching device with mainstream switching frequencies ranging from around 10 kHz to 50 kHz. Recently, new materials such as silicon carbide, SiC, gallium nitride, GaN, are being adopted as switching devices, enabling higher voltage rating and faster switching speed. These advancements have made it possible to achieve voltages in AC to DC converters for data centers and in charging circuits for electric vehicles. As such, inductors play a very important role. So the next question is, how do we know if they're performing efficiently? That brings us to the importance of measuring inductor losses, right? In today's power electronics market, there is a growing demand for smaller, lighter, and more efficient power supplies to maximize the use of electrical energy. Shown in this graph, passive components like inductors account for a significant portion of the total size and the weight of power supplies. And as overall system efficiency increases, the impact of inductor losses cannot be ignored anymore. So therefore, accurately measuring and understanding inductor losses is essential for improving design, increasing efficiency, and achieving higher performance in power supplies. So when it comes to measuring inductor losses, there are a couple of challenges we can see. One of the key challenges is the level dependence of inductors. When the input signal during measurement is large, the magnetic flux density increases and the loss characteristics change. As a result, small signal measurements cannot accurately reproduce the actual losses or behavior of the inductor. Another challenge pertains to the test setup you use. Inductance of electronic components is typically measured using an LCR meter or impedance analyzers. However, due to its measurement principle, only small signals, sound waves, can be applied, which limits the voltage and the current levels that can be used. As a result, when attempting to measure under conditions close to actual operation, like large currents, high voltages, or DC bias, can saturate the input circuit. This not only leads to inaccurate measurements, but in some cases may even damage the instrument. Therefore, while LCR meters are well suited for evaluating the static characteristics of individual components such as inductance and Q factor, they are not ideal for simulating actual operating conditions or analyzing losses during high power operation. Power analyzers, on the other hand, can directly measure large currents and high voltages and can accurately measure even in the presence of waveforms with harmonics such as PWM signals or with DC bias. This makes it possible to more accurately evaluate the losses, efficiency, and even impedance changes of inductors under real operating conditions. So next, let's look at an actual inductor loss measurement. Here you can see an example of the measurement circuit and waveforms used for inductor loss measurement. So looking at the voltage and the current waveform for the boost chopper inductor, the voltage is a square wave and the current is a triangular wave. If we check the phase angle of the current theta I1 here, you can see that it leads by about 88 degrees. The power phase angle phi 1 is also nearly 90 degrees, indicating a very, very low power factor. So under these low power factor conditions, what kind of challenges arise in measurement? So these figures illustrate how phase error in a measuring instrument affects active power readings, comparing a high power factor scenario with a low power factor scenario. When the power factor is high, that is close to 1, the impact of phase error on the active power measurement is relatively small. However, when the power factor is low, close to 0, the impact becomes significantly larger. In fact, in some cases, the phase error can push the measurement beyond 90 degrees. When that happens, power that should read as positive actually appears as negative, which is clearly a serious problem, right? So now this is especially relevant for inductor power measurements. Because the power factor of an inductor is nearly 0, the phase angle sits very close to 90 degrees. This means that phase accuracy at high frequencies, including the switching frequency, is the single most important specification to look for in your measuring setup. So let's look at how phase errors affect active power measurement. This table quantifies the impact of phase error on measured loss values. Because inductor losses involve high frequencies and low power factors, phase error can greatly affect the measurement results. For example, a phase error of just 1 degree here can result in error of about 50% in the calculated loss. Therefore, for accurate measurement of power at the switching frequency and its harmonics, it's essential to have not only flat amplitude characteristics on current sensors and power analyzers, but also flat phase characteristics over a wide frequency range. In general, current sensors tend to exhibit increasing phase error at high frequencies due to the characteristics of their magnetic cores and circuits. To address this, it's important to compensate phase errors accurately. For example, looking at this data on the right, you can see that the current sensor has a phase error about 4 degrees at 100 kilohertz before compensation. By applying the phase compensation function in a power analyzer, you can significantly improve the phase characteristics at high frequencies like the blue line in the graph and achieve more accurate power measurements. So what is the optimal measurement solution for inductor loss measurement? From here, I'll introduce some key tips and points to keep in mind when performing these measurements. And key point number one, select the right current sensor and apply phase compensation. As mentioned earlier, current sensors tend to exhibit greater phase error at high frequencies. If phase compensation is not applied, significant measurement errors can occur. So it's essential to compensate for this on the measuring instrument like this. When selecting a power analyzer, look for one that includes a built-in phase compensation function. This allows you to reduce the impact of phase error even at high frequencies. Some power analyzers also offer automatic phase compensation, where the compensated data stored in the current sensor's memory is read and applied automatically when connected. So this greatly simplifies the measurement workflow and reduces the risk of manual errors. Second key point, select the right power analyzer. Each model has its own phase characteristics, and generally speaking, newer models tend to offer improved phase performance. As you can see in the graph, the key is to choose a power analyzer that maintains small phase errors across a wide frequency range. This is very essential for accurately capturing the full range of inductor loss characteristics. Key point number 3. Consider the combination of power analyzer and the current sensor. When these two are designed as a matched pair, you can achieve flat phase characteristics across a wide frequency range, which, as we discussed, is critical for accurate inductor loss measurements. As shown in this graph, a well-matched combination maintains consistent phase performance even compared to solutions from other manufacturers. So on the other hand, if you mix power analyzers and current sensors from different brands, it can introduce significant phase errors that directly impact measurement accuracy like this. So the key takeaway here is whenever possible, use a power analyzer and the current sensor that have been validated as a recommended combination. So for today's demonstration, we'll be using this combination power analyzer, input module, and current sensor. So as we discussed in key point number 3, using a validated combination is essential for reliable inductor loss measurements. So key point number 4, connect the current sensor to the side with less voltage fluctuation. In the back chopper circuit, this means connecting it to the output side of the inductor, while in the boost chopper circuit, it should be connected to the input side of the inductor. In the case of a back chopper circuit, the voltage at the input side of the inductor changes with each switching cycle, resulting in a waveform that contains high-frequency components. In contrast, the voltage at the output side of the inductor is the output DC voltage, so there's much less fluctuation. So generally speaking, current sensors have a reduced CMRR, common mode rejection ratio at higher frequencies. So connecting the current sensor to the output side where there are fewer frequency components provides more stable measurement results. Similarly, in a boost chopper circuit, in the input side is a DC voltage, so connecting the current sensor to the input side of the inductor will also yield more stable results. So key point number 5, make sure to unify the synchronization source. When measuring a single inductor, synchronize the measurement to the inductor's own voltage or current. So during measurement, please check the channel indicators on your instrument to ensure there are no synchronization errors. So when it comes to measuring multiple inductors or the overall system efficiency, please set the sync source to either the lowest frequency or DC, depending on the situation. But the goal is to unify the calculation interval for each channel and minimize variations in the measuring results. So as with single measurements, please check the channel indicators again here during measurement to ensure that no sync errors have occurred. So 6th point, keep the voltage course as short as possible. This helps to reduce the impact of noise picked up by the voltage course and the effect of the parasitic capacitance on the measurement target. Additionally, twisting the voltage course can further minimize the influence of external noise. 7th, keep nearby conductors at a distance. If conductors carrying current other than the measurement target are placed close to the current sensor, they may affect the measurement values depending on their position. As shown in the graph here, the influence is already quite small with this sensor design, but as a general rule, it is best to arrange the setup so that cables carrying current are not placed near the current sensor. Since the impact depends on the level and the frequency of the nearby current, it's difficult to specify a strict distance. But because magnetic field strength decreases with the square of the distance, simply keeping the cables a bit away can have a significant effect. So key point number 8, make sure to center the conductor within the current sensor. When the conductor is positioned at the center, the magnetic field is evenly balanced, and the measurement is at its most stable. As shown this graph on the right, so with some current sensor designs, the position of the conductor can have a significant impact on phase accuracy. So this is something that requires careful attention in your setup. So you can also see from the data that the degree of sensitivity varies considerably between sensor designs. Some sensors show very little change regardless of conductor position, while others are much more affected. This is another factor worth considering when selecting a current sensor for inductor loss measurements. So those are the 8 key points for achieving reliable inductor loss measurements. Okay, now let's see how these principles translate into actual results. First, here's a comparison using air core coil. So air core coils don't have a magnetic core, right? So they don't exhibit level dependence, which means that LCR meter results can serve as a reliable reference for evaluating measurement accuracy. Looking at the phase characteristic on the left and the loss measurements on the right. You can see that the power analyzer results align very closely with the LCR meter reference values in these regions. On the other hand, the results from a different instrument and sensor combination show noticeable deviation, particularly at high frequencies. This is a good illustration of why the key points we discussed earlier make such a difference in practice. So next, let me share the results of measuring an inductor in a totem pole PFC circuit. As you can see in the comparison chart, the measured values vary significantly depending on the measurement approach. If phase compensation is not applied properly, the measured loss values may appear lower than they actually are, or in some cases even show up as negative, which is physically unrealistic. In practice, measurements taken with different instruments and setups produced different results. Since there is no absolute reference value for inductor loss, direct comparison is inherently difficult. But what we can say is this: when the key points we've discussed today, proper phase compensation, the right current sensor, and the validated combination, are all adopted constantly, the results tend to be more physically possible and repeatable. All right, let me now summarize everything we've covered today before I move on into the demonstration. So the 8 key points we've covered for achieving an ideal measurement solution. Points 1 through 3 are about selecting the right equipment, choosing the appropriate current sensor, power analyzer, and ensuring they work together as a validated combination. Points 4 through 8 are about optimizing your measurement setup, from sensor placement and the synchronization to minimizing noise and proper conductor positioning. So now let's put all of this into practice. In the demo, I'll walk you through an actual inductor loss measurement, so you can see how these points come together in a real-world scenario. Okay, let me start. Okay, I will now introduce inductor loss measurement. The equipment used is the power analyzer PW8001, input module US7005, and the current sensor CT6904A, bipolar power supply, function generator as a signal generator. So this is a block diagram for inductor loss measurement. So the current sensor is set by the generator like this. And now we are seeing the PW8001 screen. And measurements are displayed using the waveform stream. And monitored voltage current value here, and P1 is inductor loss. And phi 1 is a phase difference between voltage and current. Here, impedance Z, RS, series equivalent resistance RS and LS, and FU1 is a voltage frequency. And using a UDF function, user-defined function, we can calculate Z, RS, and LS. And these values are updated in real time. And there's one more point to note. On this screen, we can see IDC. So if there is a DC offset in the current and the voltage, it will result in measurement error. So please confirm that this value is sufficiently small before measurement. So when wiring for inductor measurement, please ensure that voltage is measured as close to the inductor as possible. All right. Now let's actually apply a signal to the inductor. First, we output an 100 kHz sine wave from the function generator. The signal is applied to the inductor, and the display shows approximately 32 volts to 0.1 amperes and 0.86 watt for loss. The phase difference is 89 degrees, indicating a very, very low power factor. Impedance, RS, and the LS are displayed here. From now on, we'll change the test frequency. And let's see how measurement results will change. We gradually increases the frequency in 10 kHz increment. And now 200 kHz. And 250 kHz. And we keep pushing up the frequency. And now 300 kHz. So you can see there's a stable measurement being obtained during increasing the test frequency. So currently, we are applying sine waves, 100 kHz sine wave, but next square waveform injection. Okay. And voltage waveform is now square wave, and the current waveform is a triangular waveform like this. So this type of measurement cannot be performed with an LCR meters. So it's very important to do this with power analyzers. This is considered a very important measurement. So next, we are going to see the impact of the current sensor measurements. For comparison, we are using CT6872. This is the sensors, each sensor's specification. CT6904A is a 500 amp current sensor, and the frequency ranges from DC to 4 megahertz. And the CT6872 is a 50 amp current sensor, and frequency ranges DC to 10 megahertz. Let's see what's happening. So and this is CT6904A values and CT6872 values. So you can see very small difference. And we are increasing the test frequency up to 500 kHz in 100 kHz increments. And 200 kHz, 300 kHz, and 400 kHz. So the phase difference of the CT6872 exceeds 90 degrees, and the loss becomes negative, right? So accurate measurement can become impossible depending on the sensor, as you can see. So we recommend the combination of the PW8001 with the 2005 and the CT6904A current sensor, even if you do a small current measurement. All right, thank you for watching the demonstration. Let me wrap up with the key takeaways from today's webinar. So in this webinar, we've discussed the importance of measuring inductor losses. Accurately measuring and understanding these losses is essential for improving designs, increasing efficiency, and enhancing overall power supply performance. Because inductors are level-dependent components, it's important to perform measurements under actual operating conditions using a power analyzer rather than relying solely on LCR meter results. As we've seen throughout today's session, phase characteristics play a particularly critical role in inductor loss measurement. Since the power involved is at the high frequency and low power factor, selecting a power analyzer and current sensor with small phase errors and using them as a validated combination is key to obtaining reliable results. So we hope these 8 key points we covered today will serve as a practical guide when you set up your own inductor loss measurements. Thank you very much. All right, next, we'll move on to Q&A session. Roy, over to you.
All right, Neo-san, thank you very much for the presentation. It's been very clear and interesting. But before we're going to start to the Q&A session, we will have our second poll. Please take a minute to fill out the questions, the 2 questions, or the 3 questions in this case, in the poll before we move further to the Q&A session. If you're finished with your poll, you can also answer, of course, or put in questions in the Q&A so that we can pick them up in a later stage. I see that many answers already come in the poll. So I think that we can almost close the poll and move on to the Q&A session. There are already some questions coming in. But as I mentioned, this is your opportunity to get real live answers on the questions that you might have. So please put your questions in the Q&A box, and then we can answer them immediately for you. Right. Okay, then let us continue with the Q&A session. We have a question from Ivan, and Ivan is asking, how can I perform setup validation verification? So I'm not sure what you mean with that. Is this how to set up the measurement conditions for this test? Or what do you really, if you can give us some more specific information, then we can easily answer that question for you. Second question is from Ruben, and I haven't been able to watch the entire video, and I like to be able to watch that later on. Could I ask if I have any questions via email? Yes, of course. You can answer. You will get, if you send an email to us, you will get an answer from these people if you have that question later on. Further, we have also some other questions coming in, and one of the question is that we have seen in this demonstration video that a power analyzer is being used for this loss measurement on operating conditions. It's also possible to do that with an oscilloscope. What is the difference? Who would like to answer that question, gentlemen?
Thank you, Roy. I will, I will talk to, 斉藤さん。斉藤さん、今回、ですね、デモで、実稼働状態の測定ということで、パワーアナライザーを使ったんですけども、オシロスコープをですね、使ってもできるんじゃないかっていう意見いただいてますけども、違いはオシロスコープとパワーアナライザーでやった時の違いって何なんでしょうかっていうとこ。
はい、ご質問いただきありがとうございます。質問に対してお答えいたしますが、パワーアナライザーの場合ですと、オシロスコープに比べて、温度ドリフトですとか、あとはチャンネル簡易操作っていうものがございませんので、長期間安定して測定できるのが強みになっています。またですね、オシロスコープの場合ですと、周波数ごとに位相特性が異なりますので、特にですね、複数の高周波が徴用したリアクトル損失測定の場合ですと、測定誤差に大きな違いが出てきます。
はい、斉藤さんありがとうございます。I will translate in the English. So, one of the main advantages of power analyzers over oscilloscopes is their ability to provide stable and long-term measurements without issues such as temperature drift or channel-to-channel phase differences. And also, I would say because oscilloscopes exhibit different phase characteristics at the different frequencies, measurement errors can become significant, especially when measuring inductor losses with multiple high-frequency components superimposed. And also, I would add one more comment. So, oscilloscopes, the channel has purely individual signal measured. Like when you measure inductor loss, you need current and phase current and voltage channel, right? And you need two channels, but power analyzers, so one channel has one channel contains the voltage and current input, so only single channel allows you to evaluate inductor loss. Yeah, right.
Okay, thank you for answering that question, gentlemen. Then there is another question. In the video, we have seen basically the measurement comparison with two different current sensors. We have seen the 6904A and the 6872. The 6872 has a higher bandwidth and a lower measurement range, compared to the CT6904A. But if we compared the measurement results, it appeared that the measurement with the CT6904 was more accurate and more stable than with the current sensor CT6872. Can you explain why that is?
Sure. Thank you. Thank you for your question. That is a very good point. I believe that is related to phase characteristics, but I'd like to get more in-depth answer from 斉藤さん。はい。斉藤さん、ですね、デモの動画の中で、CT6904A と CT6872、使って、測定の差を見ていたんですけども、データシート上、表示されたデータシートを見ると、CT6872 の方が、帯域広いし、良さそうなんですけど、実際には 690A の方が良かったっていう、結果だったと思います。これっていうのはどういった、なんでこういうことになったのかっていうところ、コメントいただけますか？
はい。ご質問ありがとうございます。質問に対して回答させていただきます。こちらはですね、位相補正後の、高周波領域における位相誤差がCT6904A の方が優れていることが要因として挙げられます。振幅角度のですね、周波数帯域は確かに CT6872 の方が優れているんですけれども、位相角度の周波数帯域という点で見ますと、CT6904A の方が優れているということで、今回のような違いが出たのかなというふうに考えています。
ありがとうございます。So I think this is because the CT6904A offers a better phase accuracy in the high frequency range after phase compensation. So as you can see, the CT6872 has a wider bandwidth, and meaning so wider bandwidth for amplitude accuracy. But the CT6904A excels in frequency bandwidth for phase accuracy. So that is why we got a better result with the higher current sensor CT6904A.
Okay, well then there are at this moment no new questions coming into the Q&A box. There is another question, one pending question that I have here. Can you give any tips when you want to measure board-mounted components? So accessibility of the current sensors can be, of course, challenging when you have onboard configurations. Is there any tip that you can give for that kind of situation?
All right, thanks. 斉藤さん、基板に、配置された部品の測定ですね。
はい。
それを実稼働状態を行いたいときっていうのは、なんかこう、コツみたいなのあったりするんですか？
はい。はい。ご質問に対して。基本的にはですね、配線を短く、太くするということがコツになります。で、基板実装の場合ですと、測定環境によって提案する内容も変わってきますので、こちら測定の際にお困りの際はご連絡いただければというふうに思います。
はい、ありがとうございます。So, so basically, the key is to keep the wiring as short and thick as possible. That we, explained during the presentation. But our recommendation may vary depending on your measurement environment. So please feel free to contact us if you have any concerns or questions with your some information on your measuring environment, so we can provide you more accurate answers.
Okay. Thank you very much, gentlemen, again. There are no new questions coming into the mailbox, so I think that we can close the Q&A session. Before you leave, I would like to get your attention also for some additional information that we like to share with you, and that are application notes. So on the subject, there are quite a few application notes available online, and here you find the links to those application notes. And even if you want to get a little bit more in-depth technical information, we also provide technical notes, and here you can find the links to those technical notes. And of course, when still there are then some answers that questions that cannot be answered, you can always contact us directly. And for technical questions, you can send emails to pmsupport@hioki.eu. And for commercial inquiries, you can send an email to hioki@hioki.eu. All right. That concludes this webinar for this morning. Special thanks, of course, for Nao-san and Saito-san for their support and participation in the webinar. And of course, everyone that joined, also thank you very much for participating in this webinar. All right. Hopefully see you next time. Bye-bye.